Good evening. Tonight's lecture is going to be covering entropy. This is the third out of the fourth lecture series for the thermodynamics unit. When we are discussing entropy, we are talking about the spontaneity, or more appropriately nowadays, the thermodynamic favorability of a reaction to take place, which just basically means, is it going to happen on its own? So we're going to discuss the dynamics that occur within entropy and how to calculate it in this lesson. We have a very fine line in chemistry where we're trying to look at the different aspects of a reaction from start to finish. One of the big areas that often gets confused and melded together is this concept of the thermodynamics versus the kinetics of a reaction. If you remember with the thermodynamics, we're talking about the energy changes that are occurring as a reaction moves from reactants to products. So we're focusing solely on what is the initial and the final states of the product and reactant energies. When we look at kinetics, dealing with how quickly the reaction is taking place, that's where we're looking at the different types of pathways. So we want to look at how the activation energies for the reaction determines how quickly they proceed. Looking at alternative pathways, catalytic reactions, where we have these different reactions occurring at different rates. The kinetics focuses on how quickly the reaction takes place. The thermodynamics simply tells us, will the reaction take place over time? So please do not get those get confused. When we talk about the kinetics of the reaction, that's the speed. When we're talking about thermodynamics, it's just how long it will take, regardless of the length of time. Will it happen by itself? So easy example for something like that. If you just think about the formation of diamonds naturally from coal over years and years and years, millions of years, pressure is applied to these different pieces of coal and they turn into diamonds. It is a spontaneous process, but not one that would occur naturally in our lifetimes. Entropy is a measure of the molecular randomness or disorder within a system. The driving force for a spontaneous process is an increase in the entropy of the universe. And when we talk about the universe, we're talking about the system plus the surroundings. So we're always going towards a state of more randomness or disorder, chaos within the universe. That's the second law of thermodynamics. It is a thermodynamic function that describes the number of arrangements that are available to a system existing in a given state. So you have a couple of different factors that are going to affect the thermodynamic state of the system. You want to look first and foremost at the changes in state, so going from a solid to a liquid to a gas. If you have the same states for all your different reactants and products, then you want to look at how many moles of each reactant or product you have in total in the system. So if I have the system going from 3 moles to 5 moles as a product, then I'd have an increase in the entropy. And that is nature spontaneously proceeding towards the states that have the highest probability of existing. So if I have more moles of gaseous reactants than products, then I'd have a decrease in entropy because I'm becoming more ordered, because I'd have less possible places where the products could exist. The last thing, as kind of a tiebreaker, is molecular complexity. So if I have more electrons that are present in one molecule, then I will have a greater amount of entropy compared to another. When we talk about the existence of these particles in different states or different phases, we're talking about microstates is what we call it on the chemical level. So the microstates are simply the number of possible positions. So this is where we can get into a little bit of probabilities with your math class. But you have these microstates that are just the probabilities of finding the molecules in a different type of format in a particular system. So here's an example that you can see clearly. I have 4 gaseous molecules here, A, B, C, and D. And in the first arrangement, I have the valve that is closed on a 2-valve or 2-chamber system. So I only have one possibility where I have A, B, C, and D all present in the same container. When I look at my second arrangement, having 3 molecules on one side and 1 molecule on the other, hopefully you can see that I have as a combination, I could have A, B, C, and D, each in a different compartment. If you can read the letters here, I have each of those in a different compartment, and then I have the other three that are found in the second compartment. So I have 4 possible microstates. When I go to the arrangement number 3, where I have 2 molecules in each of the chambers, now I've increased up to 6 possible scenarios where I have A, B, C, and D, AC, B, and D, AD, B, and C, BC, A, and D, BD, A, and C, and CD, A, and B, where it's just in opposite sides of the chambers. So I have 6 possible positions for those gaseous molecules to exist. I could switch to scenario 4, where I have 3 gases in one chamber and then 1 in the other. Again, just the mirror image of the arrangement number 2. So I have 4 possible scenarios. And then finally, my arrangement number 5, where I have all 4 of the gaseous particles on the other side of the chamber. When we talk about a certain process being spontaneous, that just means that it does not require any outside influence to occur in one direction. But please understand that when we look at any of these processes, if they are reversible, then if they're spontaneous in the forward direction, they would be non-spontaneous in the reverse direction. But again, as we have talked about, depending on the textbook that you're using, some of the older textbooks, you're going to see this term spontaneous being used, but please remember, don't use that term. Don't use spontaneous. What we want to use is thermodynamically favorable. Now, don't ask me why, what made the big switch. This is just something College Board did. If you want to get full credit for your problems on the free response questions, make sure that you use thermodynamically favorable instead of spontaneous. Use thermodynamically unfavorable for non-spontaneous. But as we look at these types of processes, again, something that would be spontaneous in one direction, non-spontaneous in the reverse, you can see it very easily with the dropping of the eggs. I can drop the eggs and gravity will pull it down to the floor and make them crack. But the reverse direction would be trying to take that egg that has cracked and bring it back up to your hand within the shell, and that is not possible. So a lot of times you have your spontaneous processes that will be non-spontaneous in the opposite direction. Entropy is a temperature-dependent process. When we talk about processes that are thermodynamically favorable, or again spontaneous, at one temperature, they may be thermodynamically unfavorable at other temperatures. So it is temperature dependent. The easiest thing that I can give you as an example is just a simple phase change. So if you think about the process of ice melting, if I have the temperature above 0 degrees Celsius, we don't have to do anything. So if I took a chunk of ice out of my freezer and I set it on the countertop in my classroom, because the temperature in the room is above 0, it would melt without me having to do anything to it. However, if I were trying to freeze water and I just went over to my sink and poured water into a beaker and then I set it on my countertop, because the temperature is not below 0 degrees in my classroom, despite what many of you say, it would not freeze. And so the water would just simply stay as a liquid. Once the temperature would go below 0 degrees, then the reverse process would become thermodynamically favorable, and I would have freezing that would take place. But then, because the temperature is below 0 degrees, the ice would no longer melt. So we can break down the molecular motion in terms of its entropy. Molecules can exist with or exhibit several different types of motion. We have translational movement of the entire molecule from one place to another. So when we're talking about that, you could think about that with being your liquids and your gases. We have vibrational movement periodic motion of the atoms within a molecule. So this could be just your basic bonds that are taking place between the different atoms, but you could also think about it for the molecules as what we would see taking place in your solids. And then we have rotational movement, which is the rotation of the molecule about an axis, or rotation about the pi bonds. So again, we had sigma bonds and we had pi bonds. If you remember, pi bonds are what creates your multiple bonds. So you can have some rotation about the axis, for which you have the pi bonds. But when we talk about these different types, again, the more translational movement we have, the greater amount of entropy would take place. Greater the vibrational movement that we would have, greater the entropy. Greater the rotational, greater the entropy. So finding ways to maximize the disorder increases the entropy for the system. Now let's just take a moment to discuss the positional entropy as it relates to the different phase changes that matter undergoes. So when we talk about the basic kinetic theory of matter, all the way back from like second or third grade, we know that the solids are rigidly packed together. They have no movement. They just vibrate in place, and they're very ordered. So they're going to have a very low entropy. As we add more energy to overcome those forces of attraction, again, those lovely IMFs that we always talk about, the solid particles have enough energy added to break apart from those forces of attraction, holding them together, and so they can now have that translational motion come into play, where they're able to move freely throughout the sample and just slide past one another. And then as we continue to add more energy, we eventually have the gas state that will form, where those gas particles are free to move anywhere within the container. And so again, by going from the solid to the liquid to the gaseous state, you have a large increase in entropy as you go, especially going from the liquid to that gas state. So having that condensed phase as the liquid, going to that very expanded phase for the gas, gives a lot of extra possible places where those gas particles can exist. When we talk about solutions, generally when we have a solid being dissolved in a solvent, entropy will increase. You have a very big exception, which are the carbonates. Carbonates interact with the water and actually bring more order to the system. So if you remember, your carbonates react with water, forming a bicarbonate and the hydroxide ion. Think about your salts from your acid-base unit, and so as a result, it will bring more order to the system when that takes place, and so you'd actually see a decrease in the overall entropy of the system because you have attractions for the water molecules locking them in place. When we have a gas molecule escaping from a solvent, the entropy will increase as well because, again, you're producing more gases within that system. Okay, so let's go through some qualitative problems where you can see, just by looking at the process taking place, whether or not you have a positive or a negative change in entropy. Entropy is defined as an S, so when we're looking for the change in entropy, that is going to be delta S. So as we go through these examples here, again, think about the process taking place. First, focus on phase changes. Is there a change in state of matter? If there is no change in state of matter, then go to the number of moles. If the moles are equal, then go to the complexity of the molecule. Basically, look at which one has the larger molar mass, just like we did for LDFs. So if I look at the first example, we have the evaporation of alcohol. So for that process, because I'm evaporating, I'm going from the liquid state to the gaseous state, and as a result, that is going to lead to an increase in the entropy. So gases being a higher energy state of matter, that's going to give me a positive delta S. As I look at my next example, the freezing of water, now I'm going from a liquid to a solid. So in this case, in order to form the solid, I have to become more ordered. I have to lose all that energy that allows them that translational movement. And so by doing that, delta S would be a negative value. If I'm compressing an ideal gas at constant temperature, think about what that compression does. That compression means that I'm going to have a negative change in volume. So if I have a negative change in volume, I still have a gas, but those gas particles have fewer positions where they can be found. And so due to the smaller number of possible positions, they would have a decrease in entropy. Heating an ideal gas at constant pressure. Well, if I have a constant pressure and I'm heating an ideal gas, then hopefully you recognize that that would now give me a relationship of having a positive change in volume. So not only would I have the particles moving faster, but now they also have a larger volume to occupy, so I would have a positive value of delta S. And then finally, as we just got done saying, by dissolving the NaCl in water, again, not a carbonate, so this is going to lead to an increase in entropy because as this solid dissolves, they'll be able to move the ions that are surrounded by the water molecules. They can move freely throughout that mix. So this one would also be a positive change in entropy. So you can just simply look at the reactions that are taking place and determine what the entropy changes will be, not numerically, but at least just conceptually, whether it be a positive or a negative increase or decrease in entropy. The second law of thermodynamics states that in any spontaneous process, there is always an increase in entropy of the universe. The entropy of the universe is always increasing, so we have the change in entropy of the system plus the change of the entropy in the surroundings equals the entropy of the universe. The total energy of the universe is constant, but the entropy is always increasing. This unit is very heavy on looking at the system versus the surroundings, as we've already talked about in some of our previous lectures. But when we're talking about the change in entropy for the surroundings, if it is a positive value, then that means that the system is essentially giving away energy and is causing the entropy of the universe to increase. If the delta S for the surroundings is a negative, then that means that the spontaneous process will occur in the opposite direction, and the forward direction would be thermodynamically unfavorable for that particular process. If delta S of the surroundings is equal to 0, then that process has no tendency to occur in either direction more than the other. So you can kind of think about this as it being at equilibrium. The sign of delta S of the surroundings depends on the direction of the heat flow, just like we've always talked about. The magnitude of the delta S is temperature dependent. So again, we have a larger magnitude of delta S as we increase the temperature on the system. So let's look at another quick concept check. For the process A as a liquid going to A as a solid, which direction involves an increase in energy randomness? Positional randomness, explain your answer. So pause the video again, try to answer these 3 questions, and then I'll go through the answers. So when we look at the process here, we are going through a freezing process. So when we're talking about the randomness of the particles, which direction involves an increase in the energy randomness? We're trying to go to a more energetic system, so it would be the reverse direction for this freezing process. Now, for the positional randomness, the same thing. If I'm going to a solid state from the liquid state, then the particles have a greater probability of being found in different places in the liquid state. So I'd also have the reverse direction for that. As we increase or decrease the temperature, which would take precedence for both. So again, as we increase the temperature, then that would mean that the reverse direction would have the greater application. And if we decrease the temperature, now we're removing all the energy for those particles to escape one another. So this one would be the forward direction, because as I lose energy, it's going to tend to go more towards the solid state. You can also think about this from Le Chatelier's principle kind of thing if you want to, because you know in this process, as A as a liquid goes to A as a solid, you know that it would also have heat that would be released as a product as well. So you can kind of think about it in that sense. We want to argue that based on the temperature increases and how that affects the states of matter, but you can think about it in terms of Le Chatelier's principle to kind of help you out as well. And at what temperature is there a balance between energy randomness and positional randomness? So if you think about that process, like we said, it's freezing that's going on. The freezing point or the melting point of that substance, again, the same number, just going in a different direction, that would be the point where those two things are equal to each other, or there is that balance between them. As we mentioned, delta S is a temperature-dependent process. So when we're talking about the driving force that goes into a particular reaction, it is the amount of heat that is flowing into the surroundings from the system. When we look at this heat value, we always describe the heat content as Q. So if I had a positive amount of heat flowing into the system, that would, or the surroundings, that would be the magnitude of the entropy change for the surroundings based on the temperature. So as I look at the positive Q, if this is dealing with a constant pressure situation, that is going to equal the positive value for the delta H, or the enthalpy of the system. So we can look at that temperature dependence of the delta S value as a measure of the delta H divided by the temperature in Kelvin. And so as we look at this, this will give us a very good idea based on the enthalpy of the reaction, whether or not our process is going to be a positive or a negative change in entropy. Let's now look at an example problem. In the metallurgy of antimony, the pure metal is recovered via different reactions depending on the composition of the ore. For example, iron is used to reduce antimony in sulfide ores. So we have a reaction, Sb2S3 plus 3Fe as a solid forms 2Sb as a solid plus 3Fe as a solid. The delta H for this process is a negative 125 kilojoules per mole of reaction. Calculate the delta S of the surroundings for each of these reactions at 25 degrees Celsius and 1 atmosphere. So as we look at this, the one other thing that we need to discuss, the delta S units, very similar to delta H and delta G upcoming in our next video. However, the first thing is that it is found in joules, not kilojoules. I still have the mole of reaction, but as we mentioned, it's temperature dependent, so I need to multiply by that Kelvin temperature. So that gives me joules per mole Kelvin as my final unit for delta S. You'll notice here I have a temperature of 25 degrees Celsius, so I need to add the 273, and so that would be 298 Kelvin. I have the standard 1 atmosphere for the conditions of pressure, and so to solve for delta S of the surroundings, I can simply take my delta H value, take the negative of that, so I have a negative of negative 125 kilojoules, which I'm going to convert into joules, so I have 125,000 joules, and I'm going to divide that by 298 Kelvin. So when I do that, that gives me a positive delta S value of approximately 419.5 joules per mole reaction times Kelvin. So let's now look at the relationship that we have between delta S of the system, the surroundings, and the universe in terms of their signs. So remember, the sign is just telling us the direction of change for those entropy values. So when I look at the process here being thermodynamically favorable or unfavorable, if we have a situation where delta S of the system and delta S of the surroundings are both positive, then it doesn't matter what happens, delta S of the universe must be a thermodynamically favorable process. Same thing. If delta S of the system and the surroundings are both negative, then there's no way that anything will ever occur because delta S for the universe will have to be a negative value. If I have a positive change of one and a negative change of the other, so in the situation where we have the system having a positive entropy increase and the surroundings having a negative, then that process could be spontaneous as long as the delta S for the system has a larger magnitude than delta S for the surroundings. And then finally, when we look at the delta S of the system being negative and delta S of the surroundings being positive, the overall process can occur if delta S of the surroundings has a larger magnitude than delta S for the system. When we talk about the delta S of the universe, this is where we're going to get our first lead into the free energy concept, which is the delta G for a reaction. The third law of thermodynamics simply states that the entropy of a pure, perfect crystal at 0 Kelvin is 0. Now, if you think about that, at 0 Kelvin, the whole concept means that matter ceases motion. So at 0 Kelvin, I would have no vibrational movement, I'd have no rotational movement, I'd have no translational movement. So I would have everything having a perfect 0 entropy for that system. And then secondly, the more appropriate one for us is just that relationship that the entropy of a substance increases with temperature. When we are calculating the standard entropy values, the S, remember the little knot symbol up here, degree symbol up there, just means standard conditions. So 1 atmosphere, 25 degrees Celsius. Remember, it's different from the 0 Celsius for your gases, but this will represent the entropy, increase in entropy that occurs when a substance is heated from 0 to 298 Kelvin at 1 atmosphere of pressure. So when we look at the reaction, we can have delta S for the overall reaction is equal to the sum of the coefficients times the entropies of the products minus the sum of the coefficients times the entropies for the reactants. Just as a general note here, kind of leading to that molecular complexity concept that we had talked about earlier, the standard entropies tend to increase with an increase in molar mass, and that is due to, again, the increase in the number of electrons that are moving throughout those molecular orbitals. So let's look at a practice problem where we calculate delta S for the following reaction. Again, this would be the same type of thing where you would just have a table of values that would be given to you, where you can use your equation. Delta S for the reaction equals the delta S for the products minus delta S for the reactants. So for this, the overall delta S for my reaction would be equal to the sum of my products. So I would have 2 times the 50 for the NaOH, and then I would add that to the 131 for my value for the H2. I do want you to notice though, whereas with the delta H and later on when we do delta G, you'll notice that the delta H value and delta G values have 0 for the standard enthalpy or standard free energy for the element, but notice for the entropy it actually does have a value. And I hope that makes sense because we're talking about looking at the number of positions or the amount of disorder that one of the substances can create. So my overall amount of delta S for the products is going to be 231 joules per mole Kelvin. And if I look at the delta S for the reactants, I would have 2 times 51 plus 2 times 70. So 102 plus 140, that would give us a value of 242 joules per mole Kelvin. So again, to solve for the overall delta S for the reaction, I can subtract the delta S of the products minus delta S of the reactants, and 231 minus 242, that would give me a negative 11 joules per mole Kelvin for the reaction. Okay, so that's going to wrap up the entropy concept for us for today. There will be one last video lecture which will be discussing the free energy changes that are occurring within the reaction. So please work on the practice problems on Teams and come ready with some questions tomorrow.